Namaskar, friends. Welcome to part 2 of the audiobook The Brain, The Story of You by David Eagleman. Page 7. Childhood Pruning, Exposing the Statue in the Marble. What's the secret behind the flexibility of young brains? It's not about growing new cells. In fact, the number of brain cells is the same in children and adults. Instead, the secret lies in how those cells are connected. At birth, a baby's neurons are disparate and unconnected. And in the first 2 years of life, they begin connecting up extremely rapidly as they take in sensory information. As many as 2 million new connections or synapses are formed every second in an infant's brain. By age 2, a child has over 100 trillion synapses, double the number an adult has. It has now reached a peak and has far more connections than it will need. At this point, the blooming of new connections is supplanted by a strategy of neural pruning. As we mature, 50% of the synapses will be pared back. Which synapses stay and which go? When a synapse successfully participates in a circuit, it is strengthened. In contrast, synapses weaken if they aren't useful and eventually they are eliminated. Just like paths in a forest, you lose the connections that you don't use. In a sense, the process of becoming who you are is defined by carving back the possibilities that were already present. You become who you are not because of what grows in your brain, but because of what is removed. Live wiring. Many animals are born genetically pre-programmed or hardwired for certain instincts and behaviors. Genes guide the construction of their bodies and brains in specific ways that define what they will be and how they will behave. A fly's reflex to escape in the presence of a passing shadow, a robin's pre-programmed instinct to fly south in the winter, a bear's desire to hibernate, a dog's drive to protect its master. These are all examples of instincts and behaviors that are hardwired. Hardwiring allows these creatures to move as their parents do from birth, and in some cases, to eat for themselves and survive independently. In humans, the situation is somewhat different. The human brain comes into the world with some amount of genetic hardwiring, for example, for breathing, crying, suckling, caring about faces, and having the ability to learn the details of their native language. But compared to the rest of the animal kingdom, human brains are unusually incomplete at birth. The detailed wiring diagram of the human brain is not pre-programmed. Instead, genes give very general directions for the blueprints of neural networks, and world experience fine-tunes the rest of the wiring, allowing it to adapt to the local details. The human brain's ability to shape itself to the world into which it's born has allowed our species to take over every ecosystem on the planet and begin our move into the solar system. Throughout our childhoods, our local environments refine our brain, taking the jungle of possibilities and shaping it back to correspond to what we are exposed to. Our brains form fewer but stronger connections. As an example, the language that you are exposed to in infancy, say English versus Japanese, refines your ability to hear the particular sounds of your language and worsens your capacity to hear the sounds of other languages. That is, a baby born in Japan and a baby born in America can hear and respond to all the sounds in both languages. Through time, the baby raised in Japan will lose the ability to distinguish between, say, the sounds of R and L, two sounds that aren't separated in Japanese. We are sculpted by the world we happen to drop into. In a newborn brain, neurons are relatively unconnected to one another. Over the first 2 or 3 years, the branches grow and the cells become increasingly connected. After that, the connections are pruned back, becoming fewer and stronger in adulthood. Nature's Gamble, page 10. Over our protracted childhood, the brain continually pares back its connections, shaping itself to the particulars of its environment. This is a smart strategy to match a brain to its environment, but it also comes with risks. If developing brains are not given the proper expected environment, one in which a child is nurtured and looked after, the brain will struggle to develop normally. This is something the Jensen family from Wisconsin has experienced firsthand. Carol and Bill Jensen adopted Tom, John, and Victoria when the children were 4 years old. The three children were orphans who had, until their adoption, endured appalling conditions in state run orphanages in Romania, with consequences for their brain development. When the Jensens picked up the children and took a taxi out of Romania, Carol asked the taxi driver to translate what the children were saying. The taxi driver explained they were speaking gibberish. It was not a known language. Starved of normal interaction, the children had developed a strange creole. As they have grown up, the children have had to deal with the learning disabilities, the scars of their childhood deprivation. Tom, John, and Victoria don't remember much about their time in Romania. In contrast, someone who remembers the institutions vividly is Dr. Charles Nelson, professor of pediatrics at Boston's Children's Hospital. He first visited these institutions in 1999. What he saw horrified him. Young children were kept in their cribs with no sensory stimulation. There was a single caretaker for every 15 children, and these workers were instructed not to pick the children up or show them affection in any way, even when they were crying. The concern was that such displays of affection would lead to the children wanting more, an impossibility with the limited staffing. In this context, things were as regimented as possible. Children were lined up on plastic pots for toileting. Everyone got the same haircut, regardless of gender. They were dressed alike, fed on schedule. Everything was mechanized. Children whose cries went unanswered soon learned not to cry. The children were not held and were not played with. Although they had their basic needs met, they were fed, washed, and clothed. The infants were deprived of emotional care, support, and any kind of stimulation. As a result, they developed indiscriminate friendliness. Nelson explains that he'd walk into a room and be surrounded by little kids he had never seen before, and they'd want to jump into his arms and sit on his lap or hold his hand or walk off with him. Although this sort of indiscriminate behavior seems sweet at first glance, it's a coping strategy of neglected children, and it goes hand in hand with long term attachment issues. It is a hallmark behavior of children who have grown up in an institution. Shaken by the conditions they were witnessing, Nelson and his team set up the Bucharest Early Intervention Program. They assessed 136 children aged 6 months to 3 years who had been living in institutions from birth. First, it became clear that the children had IQs in the 60s and 70s compared to an average of 100. The children showed signs of underdeveloped brains and their language was very delayed. When Nelson used electroencephalography (EEG) to measure the electrical activity in these children's brains, he found they had dramatically reduced neural activity. Without an environment with emotional care and cognitive stimulation, the human brain cannot develop normally. Encouragingly, Nelson's study also revealed an important flip side. The brain can often recover to varying degrees once the children are removed to a safe and loving environment. The younger a child is removed, the better his recovery. Children removed to foster homes before the age of 2 generally recovered well. After 2, they made improvements, but depending on the age of the child, they were left with differing levels of developmental problems. Nelson's results highlight the critical role of a loving, nurturing environment for a developing child's brain. And this illustrates the profound importance of the environment around us in shaping who we become. We are exquisitely sensitive to our surroundings because of the wire on the fly strategy of the human brain. Who we are depends heavily on where we have been. A note on Romania's orphanages on page 12. In 1966, to increase the population and the workforce, Romanian President Nicolae Ceausescu banned contraception and abortion. State gynecologists known as menstrual police examined women of childbearing age to ensure they were producing enough offspring. A celibacy tax was levied on families who had fewer than 5 children. The birth rate skyrocketed. Many poor families could not afford to care for their children, and so they gave them over to state-run institutions. In turn, the state rolled out more institutions to meet the soaring numbers. By 1989, when Ceausescu was ousted, 170,000 abandoned children resided in institutions. Scientists soon revealed the consequences of an institutional upbringing on brain development, and those studies influenced government policy. Over the years, most of the Romanian orphans have been returned to their parents or removed to government foster care. By 2005, Romania made it illegal for children to be institutionalized before the age of 2 unless severely disabled. Millions of orphans still live in institutionalized government care around the world. Given the necessity of a nurturing environment for an infant's developing brain, it is imperative that governments find ways to get the children into conditions that allow proper brain development. Page 14. The teen years. Only a couple of decades ago, it was thought that brain development was mostly complete by the end of childhood. But we now know that the process of building a human brain takes up to 25 years. The teen years are a period of such important neural reorganization and change that it dramatically affects who we seem to be. Hormones coursing around our bodies cause obvious physical changes as we take on the appearance of adults. But out of sight, our brains are undergoing equally monumental changes. These changes profoundly color how we behave and react to the world around us. One of these changes has to do with an emerging sense of self and with it self consciousness. To get a sense of the teen brain at work, we ran a simple experiment. With the help of my graduate student Ricky Savjani, we asked volunteers to sit on a stool in a shop window display. We then pulled back the curtain to expose the volunteer looking out on the world to be gawked at by passerby. Before sending them into this socially awkward situation, we rigged up each volunteer so we'd be able to measure their emotional response. We hooked them up with a device to measure the galvanic skin response GSR, a useful proxy for anxiety. The more your sweat glands open, the higher your skin conductance will be. This is, by the way, the same technology used in a lie detector or a polygraph test. A note on the sculpting of the adolescent brain on page 14. After childhood, just before the onset of puberty, there is a second period of overproduction. The prefrontal cortex sprouts new cells and new connections, synapses, thereby creating new pathways for molding. This excess is followed by approximately a decade of pruning. All through our teenage years, weaker connections are trimmed back while stronger connections are reinforced. As a result of this thinning out, the volume of the prefrontal cortex reduces by about 1% per year during the teenage years. The shaping of circuits during the teen years sets us up for the lessons we learn on our paths to becoming adults. Because these massive changes take place in brain areas required for higher reasoning and the control of urges, adolescence is a time of steep cognitive change. The dorsolateral prefrontal cortex, important for controlling impulses, is among the most belated regions to mature, not reaching its adult state until the early 20s. Well before neuroscientists worked out the details, car insurance companies noticed the consequences of incomplete brain maturation and they accordingly charge more for teen drivers. Likewise, the criminal justice system has long held this intuition and thus juveniles are treated differently than adults. Both adults and teens participated in our experiment. In adults, we observed a stress response from being stared at by strangers, exactly as expected. But in teenagers, that same experience caused social emotions to go into overdrive. The teens were much more anxious, some to the point of trembling while they were being watched. Why the difference between the adults and teens? The answer involves an area of the brain called the medial prefrontal cortex, the MPFC. This region becomes active when you think about yourself and especially the emotional significance of a situation to yourself. Dr. Lee Somerville and her colleagues at Harvard University found that as one grows from childhood to adolescence, the MPFC becomes more active in social situations, peaking at around 15 years old. At this point, social situations carry a lot of emotional weight, resulting in a self conscious stress response of high intensity. That is, in adolescence, thinking about oneself, so called self evaluation, is a high priority. In contrast, an adult brain has grown accustomed to a sense of self like having broken in a new pair of shoes, and as a result, an adult doesn't care as much about sitting in the shop window. Beyond social awkwardness and emotional hypersensitivity, the teen brain is set up to take risks. Whether it's driving fast or sexting naked photos, risky behaviors are more tempting to the teen brain than to the adult brain. Much of that has to do with the way we respond to rewards and incentives. As we move from childhood into adolescence, the brain shows an increasing response to rewards in areas related to pleasure seeking. One such area is called the nucleus accumbens. In teens, the activity here is as high as it is in adults. But here, the important fact, activity in the orbitofrontal cortex involved in executive decision making, attention, and stimulating future consequences is still about the same in teens as it is in children. A mature pleasure seeking system coupled with an immature orbitofrontal cortex means that teens are not only emotionally hypersensitive but also less able to control their emotions than adults. Moreover, Somerville and her team have an idea why peer pressure strongly compels behavior in teens. Areas involved in social considerations such as the MPFC are more strongly coupled to other brain regions that translate motivations into actions. The striatum and its network of connections. This, they suggest, might explain why teens are more likely to take risks when their friends are around. How we see the world as a teenager is a consequence of a changing brain that's right on schedule. These changes leads us to be more self-conscious, more risk-taking, and more prone to peer-motivated behavior. For frustrated parents the world over, there's an important message. Who we are as a teenager is not simply the result of a choice or an attitude, it is the product of a period of intense and inevitable neural change. We have come to the end of this part. This is page 17. Keep listening, keep growing, stay alive. Thank you. Gratitude to all listeners. God bless you.